Hello, welcome to part three of our series of lectures on volcanoes. Okay, so let's go straight in there. To summarize all the volcanic hazards we covered in the last lecture, we'll use this slide again, this image, so you can see many of the ones we've talked about and learned about, such as um, pyroclastic flows, lava flows, poisonous gases coming out of escaping from these fumaroles, ash fall from the volcanic plume above, which can cause acid rain as well, and landslides as well. There's a few others we didn't talk so much about. And importantly, lahars. Remember, lahars can happen during the eruption or straight after the eruption, often from snowmelt, but also at any point during the year. When all that unconsolidated ash can be mixed with heavy rain, which is why lahars are frequent in the tropics, and produce a mudslide, a very deadly mudslide. All right, moving on. So we're going to go back to those series of questions you can ask about all hazards or things in hazard analysis. So we're up to the middle here in red. So how often is the next question we're going to answer. How often does, in this case, volcanic eruptions, do they occur? It's something called the recurrence interval, which is how often on average does this specific volcano erupt? Is it every decade? Is it every century? Is it every 1,000 years? And then we move through the other questions, important ones to us as a society, as individuals, as communities. How can we make a long-term forecast for volcanic eruption? What's the likelihood of a large eruption over the next, couple of decades, for example? And then, importantly, can we make a short-term forecast? When is it going to happen? Is it going to happen next Sunday? That's going to be, let's get out of here. Then we'll move on to what are the signs for that? And there are actual signs. We can actually do some short-term forecasting. We'll find out. Who's at risk? We can produce things called hazard maps to zone basically areas around a volcano, which areas are of a higher risk for specific hazards often, be they ash or lava. And what can we do about it as well? Something called mitigation. How can we lessen the risk? Okay. Okay, so first of all, this this key thing called recurrence interval, which relates to long-term prediction. And to help you understand this theme of recurrence interval, here's a graph on the left, which shows recurrence interval for river floods. So you may have heard on the news, maybe you haven't, maybe you have, of things called 50-year floods or even 100-year floods. Basically, it's a type of very large flood that typically for that river only occurs, fortunately, every 50 years or every 100 years or more frequent ones like every 10 years. So this graph shows the recurrence interval plotted. So for these floods, say 50-year floods, they could manage the gauging station on the river, the annual discharge, so here it is in cubic meters per second, the amount of volume of water flowing past this gauging station. On a 50-year flood, it's for this specific river, it's 2,500 cubic meters per second of water. So let's take it, that's a very large amount for that river. How often does that river fill its banks, or right to the brim, if you will, a very fast flowing water? Every 50 years. So there's every 50 years you typically have this kind of volume of water. And then you can plot all the data, if you got the river history, the hydrological data available, you can work out the recurrence intervals for different size floods, be it a 10-year flood, 50-year flood, or every year, the annual flood. You can do the same thing for just about any hazard. Today we're talking about volcanoes, so you can do what's the recurrence interval, for how often do these large volcanic eruptions take place? Say a very large eruption, I'll take you back to that VEI scale, the Volcanic Explosivity Index scale. So how often does a VEI 6 eruption take place? How often does a VEI 3 or a smaller eruption take place, etc. The key thing here, it says on the bottom right, is big events are rare and small events are common. So big events are generally are longer spaced apart. And typically for volcanic eruptions, If it doesn't erupt, your volcano very infrequently, generally you're going to have large eruptions when it does go off. Okay, so how is recurrence interval determined for volcanoes in this case? It's all about looking at the past and building up that history of eruptions over as long a time scale as you can find, and as you know, the higher resolution as you can do. So the key phrase here is the past is the key to the future. Use that in geology for all sorts of things. Basically, if you work out what's happening in the past, you can extrapolate that to the future. You can say the past is, you know, that is typical for that volcanic eruption frequency for this volcano. Therefore, you can safely say that it'll behave in the same way in the future. And we use this in all sorts of things in geology. This key thing. So how would you build up your recurrence interval history? But basically, you can look at different sorts of records of eruptions on different time scales. So you can firstly at the modern records. Here you're thinking, you know, active volcanoes now during the last century, say. So how often are they erupting, for example? Historical records. So you now want to go back into the historical documents. So that may take you back several centuries. And these recorded eruptions in history. Once you do kind of, you know, the literature research, you can build up a history for your volcano or your volcanic region. This historical records vary depending on where you are in the world. Historical records, for example, for North America may only go back 300, 400 years, or at most. But then for places like Italy or China, some of those records go back many thousands of years that have been documented. So before historical records, prior to those, existence of those, you need to go back into the geologic history. So you need to find physical evidence on the ground for a former volcanic eruption. So you look at things as a geologist, things like ancient lava flows, and you map them out, and you kind of where are they? Ash deposits, pyroclastic flow deposits, usually this sort of tumble of different sized particles. And you look through the stratigraphic record. Basically, as you go, the stratigraphic record is a history layer by layer. As you get deeper, you get older typically, and through those layers in the stratigraphic record, you try to date these events, which isn't always easy, but there's different techniques you can use to date ancient lava flows, for example, or ashfall deposits. Generally, you use some radiometric methods, so isotope dating of eruption, so using things like radiocarbon dating. So basically the amount of the radioactive isotope carbon-14 that's left, that's remaining, and that gives you a clue of the ratio of unstable to stable isotope, gives you a clue of how old. It's a technique basically to date things, of how old organic material is. So for radiocarbon dating, you need organic material. Therefore, sometimes in lava flows or ash deposits, trees, bits of organic material may get a large incorporated and not consumed, if you will, not incinerated, but certainly the ash from the charcoal from them, and you can date that carbon. You can get a date on that carbon, a radiometric date. Also, often when lava flows or ash flows, they cover an area of ground. So you have soil, a former ground surface with now a lava flow on top. You date the top of that soil horizon, basically, where the former ground surface was, so the grass growing. And that thin organic layer at the top of that soil is something called a paleosoil, an ancient soil. You can take samples and radiocarbon date. So there's different ways you can do it. And you build up a history. And then from all these types of records, you have a history for your volcano. And some volcanoes, just you realize, can be quite long-lived, if you will. Mauna Loa on Hawaii, remember we learned it's on a hotspot. It's been there, it's been there for going up to sort of 1 million years. So some volcanoes have been there. So you've got 1 million years of eruption history to work through. Here is some deposits. In this case, these are lahar deposits, so ancient volcanic mudflow deposits from Pinatubo. So we've talked about historic eruptions. Pinatubo was the second largest eruption of the 20th century back in 1991. Huge eruption. But it's also been a very active volcano for many, many thousands of years. And this one in the photo here is actually an ancient deposit, many centuries old. And here you can see the very thick deposit of lahar debris. So this big jumble of material that came down the valleys on the flanks of Pinatubo. In this case, maybe centuries or a couple of thousand years ago. I'm not sure on the date on this, but and this can be dated though. It will incorporate bits of organic material in, so you can date this lahar. You do that for say for Pinatubo, and you date all, and you work out from the areal spatial thicknesses of the deposits and how spatially far from the main crater they are, and you can work out kind of how explosive that event was and put it on the VEI scale, approximate it on the VEI scale. So it could be from a 1 up to 6 or even more, the very, very explosive eruptions. You plot all that data. Hopefully the more data, like always in science, the more data the better. And you say, for example, here it shows on the graph here the interval between eruptions. Typically every sort of 1,000 years you may have a VEI on the sort of 5 or 6 very, very explosive eruptions. Every century may be a VEI 4, but every decade it may be small eruptions. This record, by the way, is not for Pinatubo, but it shows you the principle. So how can we make a long-term forecast? Well, it's really to do what we've just been talking about. It's to do with recurrence interval, typically for volcanoes. So here, and linking recurrence interval of different VEI type scale eruptions. So how often do large eruptions take place on the VEI scale? Moderate eruptions, small eruptions. Build a history, plot them on a graph like I just showed, and that tells you, the recurrence interval. Then finally, for each style of eruption. I'm not going to go through this graph. We've done this before, so but just to briefly, volcanic explosivity index from 0 or 1 up to sort of 7, typically very, very rare. Only a couple in the last 1,000 years worldwide. But this data is actually for the numbers here are for a study of all historic eruptions, kind of worldwide. So they've shown how often these very large eruptions take place, and moderate eruptions on Earth take place, and small eruptions take place. Put all that data, historic data, on this graph, and it's really showing what I showed just a couple of slides back. The very large eruptions of VEI 5 and 6, for example, or even 7, typically only occur every 1,000 years, or most every 1,000 years. You may get a few, say VEI 5 every century, but generally we're speaking every 1,000 years. So you plot histograms for each of these VEI scales, and again, maybe every century for your VEI 4 worldwide, and then sort of decadal for these small eruptions. You see these small eruptions on your news screens often. Whichever typically year you're looking at. The United States. So here's examples of the eruption histories of various volcanoes in the Cascade Mountains. The volcanic mountain range in the northwest that runs from northern California through Oregon and through Washington State. And here you can see there's this whole list of active volcanoes, be it Mount Shasta in northern California, the Three Sisters volcano, Mount Jefferson in Oregon, or Mount Helens and Mount Rainier in Washington. And here shows these little diagrams show when a major eruption took place. So, for example, you can see Mount St. Helens is a very, very active volcano. It erupts typically, this is a 4,000-year record, but it typically erupts, at least every century. Typically, or certainly every century, you have a large eruption in Mount St. Helens. Recurrence interval doesn't mean it's going to happen every 100 years, like clockwork. It typically means on average. So you may have one, the last one was 1980 in Mount St. Helens, and maybe one next year, or in the next few years. Or it could be another 130 years, but on average over a long time scale, it's let's say the recurrence interval is every 100 years. Other volcanoes in the Cascades, let's say Mount Hood, the record here, typically, more than every 1,000 years between each eruption. as we'll learn though, or as I'll say now, when these recurrence interval is longer, typically a longer time between eruptions. Typically, it goes off in a big way. Mount Pinatubo actually doesn't. It's been very active for a long, long time, but the actual recurrence interval is quite large. So it has very large eruptions when it goes off. Same for Mount Hood here. Mount Shasta in Northern California, typically every few centuries. Slightly less infrequent than Mount St. Helens, for example. Okay, so we have these. We can see where the active volcanoes are. We know that they do erupt sometimes every decade or every more likely every century or so. We know they're a threat. We went through the hazards. Very lethal, dangerous threats. They pose a risk to people, to property, in terms of lava flows and ash. So why do people live near volcanoes? Firstly, many volcanoes harm no one. Some are dormant. Some are, extinct almost. Or some have a very long recurrence interval. So they, typically they don't erupt. Maybe every 300, every 400 years, you have a significant eruption. And human perception of risk generally is on a shorter time scale. It's generally, within one generation in terms of sort of a few decades at most. Going back centuries, before your existence, before your parents' time, before your grandparents, you might have read about a large eruption too in the history books 200 years ago, but it's not in your concept of life in that spot and what happens to that mountain on the horizon. It's pretty safe. So that's why people don't, they think it's low risk. They may be correct in thinking that, depending on the volcano. But so like I say, it's perception of risk. Volcanoes are often on the coast. Most people live on the coast in the world. Something like 40% of people live within 100 miles of the coast, 100 kilometers of the coast, which might seem a long distance, but it's actually still quite a narrow zone. Why? Because most geohazards like volcanoes and earthquakes occur on the coast. So therefore, you kind of, most cities historically have been placed as ports, etc., on the coast. That's where most people live. But that's where these geohazards exist, are located due to plate tectonics mainly. So there's no way getting away from them essentially. Countries like Japan are basically a volcanic island range, volcanic islands. There really is no safe spot. Oregon and Washington, you're right beside the Cascades on the coast there, near a subduction zone, convergent plate boundary, and there's always a ever-present danger of eruptions in these places. Why do people live near volcanoes? It's often for things like agriculture. Volcanic soils are very fertile, very fertile. Basically, it's been shown they've got lots of sort of minerals, some ashfall, etc., which are very good for plants and for growth, and therefore they can put the yield, the annual yield of your crop up twofold or even threefold if you have your farm on the flanks or within a certain radius of the volcano. So they're very good for crops like coffee, maize, rice, pineapples here, the list, sugarcane, grapes, and many places around the world, especially in say the Southeast Asia, Central America, where some of these crops are more common. So yeah, if you're a farmer, this volcano doesn't erupt, hasn't in your lifetime. If you have a chance to have land on that fertile soil, you're gonna grow crops there and live there. Geothermal energy, another reason, more relevant to some countries in the world, depending on how they're using this energy. But places like Iceland or New Zealand, very volcanically active countries, people use, they use energy based on that heat underground, and they create energy, geothermal energy. So it's the pros outweigh the risk there of living and producing energy in that area. Recreation, many volcanoes are large mountains, or they're very picturesque. They're parts of mountain ranges like the Cascades or like in Northern California, and they have everything associated with the great outdoors, be it for hiking, for boating or on lakes, or etc. So there could be location for health spas. You may have hot springs associated with them, people visiting them for the hot springs. So hiking, skiing, these mountains have high elevation, so you have snowfall at winter, heavy snowfall, and therefore a ski industry. So big recreation industries often around these mountains, these volcanoes. And lastly, but not least, hey, it's Hawaii. Who wouldn't want to live in Hawaii? One could ask. So yeah, I'm going to move to Hawaii. There may be active volcanoes there, but hey, it's a lovely place to live. All right, yeah. So hey, it's Hawaii. It reminds me, just an aside here, showing my musical taste here. A band called AC/DC, an old metal band, heavy metal band. Both two lead singers of that actually live on Hawaii now. British guys like myself, but they both live on Hawaii because hey, it's Hawaii. Okay, but something to bear in mind. At the bottom here, Japanese proverb: natural calamity strikes about the time when one forgets its terror. Again, going back to that human perception of risk. If it doesn't happen very often, you kind of forget there's that risk on the horizon. But when it does strike, often it can be, calamitous, catastrophic even. Okay, moving on to the next question. So how can we make a short-term forecast? Are there signs a volcanic eruption may take place in the next week, in the next few days, for example? And these things are called precursors, these signs, precursors, something that is happening in a volcano that tells you, the observer, tells you, the scientist, the geologist, that something is about to happen. That volcano is awakening. Be warned, a volcanic eruption may take place. So let's just list some of these precursors. Ground tilt. So beneath volcanoes, magma, all volcanoes have a magma chamber beneath them, and often prior to an eruption, that magma chamber from deeply sourced magma will fill up essentially, and the magma will rise underneath the volcano and maybe come up some of the up through the vents, and that will cause the volcano itself to actually physically bulge, literally. And if you have instruments on the mountainside that measure, say, for example, the tilt of that mountainside, it will get a steeper angle as that volcano bulges out due to the magma inflation underground. Earthquakes, a very important one, and often a very common sign that something may or may not, they're not infallible, these things, may or may not happen as far as an eruption. So earthquakes, shallow earthquakes and swarms can often, so many earthquakes can often precede an eruption. They're often quite small earthquakes. You might not even feel them if you were there, but sometimes you will, though. But if you have an instrument called a seismograph, a seismometer, you can then measure, the ground vibrations, even very small ones. And sometimes, or very often actually, you have these swarms of earthquakes just prior to an eruption. We'll come back to some of these ones, by the way, in the next couple of slides. I'll show you some images. May not provide enough time for evacuation, though. Sometimes these earthquakes only start kind of getting going in the last 24 hours. You really need good time. 48 hours would be preferable before, to really get everyone out of an area. Temperature changes, more magma underground, getting close to the surface. You can actually use, instruments to measure temperature of the ground and groundwater, and it shows a rise in that temperature. Thermal monitoring, you can indicate possible imminent eruption. You can do that actually by satellite or by aerial remote sensing of the ground from a flyover. So you can do this in all sorts of ways, just to constantly monitor an area. Changes in volcanic gas emissions. So if you're monitoring or taking samples, or constantly monitoring in some cases, volcanic gas emissions from fissures and from the main vent itself, etc., or from side vents, fumaroles, you can pick up an increase in the amount of these volcanic gases. For example, carbon dioxide concentration increasing, or sulfur dioxide, hydrogen sulfide, all those gases that can be emitted from volcanoes. So again, if there's a rise in those gases, it's a warning sign, a precursor. Ground or aerial magnetic survey. So again, this can be done very quickly from the air. and you basically have a magnetometer, and you can see if the change in the magnetic signal from the ground. If you're introducing more magma, slightly different type of rock into an area, the magnetic signal of that ground will change. Again, another technique to use for looking at this. So just to show you a couple of those things, just a couple of images relating to some of those precursors. Here's the one on ground tilt and displacement. So here's a historical photo. This is from a long time ago of a scientist measuring the tilt, one of the very earliest tilt meters. They're a lot smaller now, but here you can measure the tilt of the inflation of this mountain. So you can see here on the right, stage 1, inflation begins, gradually more inflation, the mountain will bulge, and then you have if you look on the slides, the eruption, that magma chamber evacuates some of the magma and the lava, and it'll then collapse in on itself, and it'll sink back down, deflate. Here you can see this inflation and deflation cycle. This is from Mauna Loa, a record from the 1960s for measurements. So here you can see an eruption from 1965, early that year, then later, at the end of that year, December 1965, another eruption. But you can see they were measuring the tilt of the sides of Mauna Loa. You can see it gets steeper and steeper, and then deflate. So it's inflation, deflation, this cycle, which often happens prior to each eruption on volcanoes like in this case, Kilauea, sorry, not Mauna Loa. You can use measures in surface elevation. So rather than have a sort of tilt meter, better ways now are really to use GPS. This is again a few years old, this image, but here they've actually flown to the top of a volcano in the Cascades, and they've set up what's called a base station, and they'll be measuring surface elevation. GPS is typically, can measure within 1 or 2 centimeters accuracy, a high precision GPS anywhere on Earth, linked to an array of satellites above. Typically these days, I do a lot of surveying as part of my field work, and you don't need large. The modern GPSs now, especially in the last sort of 10 years, don't need these large base stations anymore. You can do it all as long as you're within a phone network coverage, mobile, cell phone network coverage. You could you can link into that to help, and then you can actually just need one thing, one pole, and you can beep, 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 and it'll give you the elevation of the ground wherever you are. So if you monitor the elevation constantly, or every whatever frequency of time, you can see changes again to tell you, hey, that side of the volcano seems to be inflating, guys. Let's watch out and look for other signs, other precursors. Here's an image of a guy with a magnetometer, a geophysical device, who will be doing a magnetic survey of an area. Okay, earthquakes. So here in the northwest, in the red circles, are active volcanoes in the Cascade Mountains. So from, for example, Three Sisters, Mount Jefferson, Mount Hood, Mount Adams, Mount St. Helens, Mount Rainier. So in Oregon and Washington states. All the green squares are seismograph stations. So they're monitoring the ground for ground vibrations, for seismic waves, so for earthquakes. Not so much, actually, this network wasn't principally put in for the volcanoes, but it's used for volcanic prediction. But it was there because you get also large earthquakes there due to the very nearby subduction zone. And you have what's called the Pacific and the Juan de Fuca plate, which is subducting underneath the North American plate here, and you get very sometimes shallow near the coast, but then quite deep rooted earthquakes. And you can the seismic network can quickly locate, as we'll find out when we talk about earthquakes, the location of those earthquakes very quickly, tell you straight away where that earthquake is taking place. But the same network can be used to monitor earthquakes, smaller earthquakes, shallow earthquakes related to magma movement beneath these volcanoes. So when volcanoes awaken, here you can see the graph on the bottom left, as magma starts to come up the main vent and build up in the magma chamber beneath the volcano, a lot of stress and fractures are created and causes small earthquakes. As I say, many of them too small for you to feel. Some of them you will, but a lot of them you just a very sensitive instrument like a seismometer will detect. But here on the bottom graph, you can see the days before the eruption. So 16 days on the left and 0 on the right hand of that graph. And very slow increase in earthquakes per day. So no, we're in large numbers, 500, 1,000 earthquakes per day. But after, say, 5 days before the eruption, they start accelerating the numbers. And certainly after 2 days, you start to get a very noticeable amount of earthquake swarm, as they're called. And that tells you something's going on underground. The magma is on the move. We need to take action and evacuate the area if it gets to that stage. So how well do these precursors work as far as predicting a volcanic eruption? Well, there are success stories. It's almost 50-50. I'm not sure of the actual figures, but there are success stories. For example, Mount Pinatubo, the second largest eruption of the 20th century, really most powerful eruption of recent times, certainly the last 100 years. Happened in 1991 in the Philippines, Southeast Asia. Huge eruption, 12 times bigger than Mount St. Helens, 12 cubic kilometers of material ejected. Massive eruption, quite densely populated islands of Philippines, and scientists were flown in quickly once the local scientists and the local Filipino government noticed a few warning signs, and more scientists, US Geological Survey scientists, were flown in from the United States, and they started monitoring that Mount Pinatubo intensely. And combined with the military there, at that time in 1991, there was a US naval base and a US Air Force base based in the Philippines at that time. And the US personnel, US military personnel, and the scientists collectively with the local government predicted the volcanic eruption based on precursors like earthquakes, the increase in earthquakes, like gases increasing, the temperature increasing, the mountain inflating, etc. And there was a very, very, very successful evacuation of something like 200,000 people from a radius around the earthquake, and that saved literally tens of thousands, if not hundreds of thousands of lives, because when it did go off, because it did, it was huge, a cataclysmic in size eruption, but the death toll, there were some unfortunately, but was much less than it would have been without these analysis of precursors. Next. Okay, not every story is a success though. Sometimes sometimes basically there is no precursors. Sometimes the volcanic eruptions just go off and there are no precursors, or there are no signs. That volcano does not give you a warning sign, but it still erupts. Quite recently, about 5 years ago now, in Japan, there was what had been quite dormant or very infrequent eruptions of a volcano. People thought there was no danger, and on the day of the eruption, there happened to be many hikers up there on the flanks of that volcano on a guided walk up this mountain, and the volcano erupted. Not a huge explosive eruption. What unfortunately killed all of this group of these hikers, was the ashfall, and it came down in very thick quantities, and they did not have masks on them, so they ingested, breathed in all this very sharp volcanic glass, which is what ash is, and they perished because of that. If they had masks on them, some, maybe all, could have survived. It's a tragedy there. But anyway, there was no sign that volcano was going to go up. Sometimes there are precursors, there are signs, warning signs, but then no eruption. It doesn't happen. And that actually that's not uncommon to happen. Famous example in the United States, within California, at the Mammoth Lake volcanic area, and here a large caldera floor of this large ancient caldera type volcano. And remember, calderas, when they go off, are huge. They're the largest, most violent type of eruption. It began to bulge, inflate, and were quite large. Certainly, absolutely, you could feel these earthquakes. Magnitude 5 or 6 earthquakes were occurring. that to me, as a geologist, or even as a bystander, you'd say, once you'd heard these things were happening, you'd think, let's get out of here. And the US Geological Survey did. They issued a low-level alert. Mammoth Lakes is a big tourist area for skiing, for hiking, everything else. And the resorts closed down. Thousands of dollars, millions of dollars maybe, of revenue was lost, but there was no eruption. So there was a lot of slightly annoyed CEOs of all these tourism um, industries around that area because they lost a lot of money because of it. But you have to assess the risk, and I think the scientists made the right decision, and the local government made the right decision by causing that evacuation at that time, because there could well have been an eruption. At this point, it's to do with earthquakes, but I think I'll just mention something related to that, where sometimes precursors are no eruption, or sometimes, sometimes scientists say there's very low risk, and then something does happen. So they get it the other way around. For example, to do with an earthquake in Italy in 2009, there's signs of possibly being an earthquake. Scientists at the time said pretty much said at the time kind of made reassuring statements to the public that there was no chance of an earthquake, or very low probability. As we'll learn when we talk about earthquakes, it's actually incredibly hard, if not impossible, to predict an earthquake, by the way. Anyway, back in 2009, there were signs of an earthquake, possibly. Sometimes, occasionally, there are, but scientists said there's very low probability. There was an earthquake. 29 people lost their lives. Those scientists were sentenced to and charged with manslaughter for giving out the wrong, falsely, warning or lack of warning, and they were sentenced to 6 years in prison each, simply for doing their job. And finally, though, their decision, that court order, was overturned in appeal, and they didn't go to prison. But a huge amount of public kind of outcry and kind of poison pen letters against these scientists. They still thought these people were to blame, but they were doing their job. We have to assess the risk at the time, and as we'll find out with earthquakes anyway, there's almost impossible to detect earthquakes. A lot of research goes into it, but at the moment, there's very few precursors that kind of are reliable. Okay. Finally, who is at risk? Almost finally, who is at risk in an area? Well, that's where we produce a hazard map. So we know we map the risks of in terms of high risk, moderate risk, low risk of danger to yourself or your property from a volcanic eruption. Here on the main island of Hawaii, the highest risk, the darkest blue, near where you'd think there would be, near the two active volcanoes of Kilauea and Mauna Loa, along these sort of long fissure type eruptions. And then gradually away from that vent and fissures, the risk decreases. So the risk of that hazard occurring decreases with the way. So you have a hazard map. Here, also in the United States, here in Washington State, related to Mount Rainier, the active volcano Mount Rainier in the Cascade Mountains. Here's a hazard map produced by the United States Geological Survey, the USGS. And the blue, for example, nearest to the mountain itself, is for lava flows and ashfall. But then further away down these river valleys, rivers flow out radially from volcanoes often. These can act as conduits for lahars, volcanic mud flows, when you have an eruption, or just in between eruptions from volcanic lahars occurring. So they've mapped out and dated all these ancient lahars, so therefore they can work out the risk, how frequency, what's the recurrence interval of a very large lahar, or a moderate lahar, or a small lahar. Here it shows the small ones less than every 100 years they occur, moderate ones every 1 to 5 centuries, which might sound a long time, but when lahars do happen, they can be completely deadly and cause huge numbers of deaths. So all these towns like Orting, if I highlight that here, Orting down the river here, down the, I think it's the Payulup River. They have action plans, emergency planning to evacuate their town if there's an impending lahar coming down the river. How do they know? Well, certainly near Mount Rainier, there's actually a lahar set up in the 1990s, a lahar warning system, and all the way up these valleys, they have pressure sensors the bottom of the valleys, which can detect the movement of this very high, dense tumble of mainly rocks with a little bit of water in. So very viscous mud flow moving across. Very different signature, if you will, from a normal water river flood. And it gives you warning, therefore, if you're downriver, depending on how far away you are from the sensors, 30 minutes, 40 minutes, maybe an hour at most to do. So 30 minutes, 40 minutes, hopefully you have an immediate warning to the local residents to get to high ground. They'll know where they have to go. They'll have done routines, maybe at school, in their workplace, of what they should do in case of something like this. On a larger kind of spatial area, here's the volcanic hazards of the United States. It's where you'd expect them. Volcanoes that occur along sort of inland away from the subduction zone, which is offshore from Washington and Oregon State. And that's where these volcanic plumes, if you remember, come up through the Earth's crust and lithosphere, and you get this chain of volcanic mountains. Also, ashfall, ash effects shown in here in grey. The hazard from the ash obviously will affect a larger spatial area away from the volcano. If you read this, this typical kind of alert levels information, which are in some parts of the world, these are set up. They're certainly in the northwest of the United States. You have these, for example, the alert levels are on ground level, normal. The volcano's not doing anything really. It's a non-eruptive state. Then there's an advisories and watches. For example, watches the volcano is exhibiting heightened or escalating unrest with increased potential eruption. Or the eruption is underway but poses limited hazard. So it's a lot. The first part is often to do with these precursors, warning. The final, the highest level of alert, hazardous eruption is imminent, underway, or suspected. Evacuate is the key there. Or move to a predetermined safe location. For aviation, so the aircraft, they have a very similar warning system, green, yellow, orange, red in colors now, basically to avoid an area of a possible or imminent or actual eruption, so they can take different flight paths. Finally, what can or what should we do about it? Well, so this is all about the keyword mitigation. So mitigation, to define it, firstly, the word is and this is from FEMA, the Federal Emergency Management Advisory, is the US government agency. So mitigation is the effort to reduce loss of life and property by lessening the impact of disasters. What actions can we do to lessen the risk to us from a lava flow, from an ashfall, etc.? So to list just a few of them, live somewhere else is one. But unfortunately, in some countries like Japan, or the highly populated islands of Southeast Asia, for example, or even parts of Italy, near Mount Etna, for example, there's large cities. You really can't move at this point away from these hazards. Evacuate. That's certainly a very important type of mitigation. It will reduce loss of life, absolutely. Not loss of property, unfortunately, but certainly loss of life. So that is certainly a pathway to think about. There is a risk of false alarms, as we talked about. For non-explosive lavas, people have tried, so not an explosive eruption, more kind of a Hawaiian or Icelandic type eruption. You can build barriers to redirect these lava flows. Can we actually divert that lava flow away from our town, away from our community? And they often, these lava flows, these streams of molten rock, sometimes these local communities do attempt to do this. Another way of stopping a lava flow, red hot lava flow, is can we cool it down? Turn it back into a rock, lower the temperature down to below the melting point of that rock. So you can simply spray with hoses huge volumes of water onto that lava flow, and hopefully with the aim of cooling it down by water chilling. Almost never happens, never works out, that one. You need huge quantities of water to cool down a molten, huge volume of molten rock, massive amounts. So it's usually done in vain, but people usually want to try something, and occasionally, as I mentioned, certainly one example where it did work, but it's very, very rare. Map the hazards firstly, know the risk, zone it into different areas of high, moderate, and low risk. Therefore, you can plan where you build certain parts of your community, certain types of property, be it just commercial property or residential property in certain areas. or not build at all, obviously. Here, the example where water chilling did work. Very few examples. One of the very few examples where it did work was in Iceland, volcanic island in the North Atlantic. Here, off a small island off Iceland, Jaime Island, there were lava flows from an eruption back in 1973. They were threatening this fishing port, so that all the livelihoods were at risk from the harbour being basically consumed by lava. So what they did is they got hoses of water directly from the ocean and started spraying it. So they had that source right beside them where they could spray water directly on the lava flow. Because of that easy proximity, they actually did stop the lava flow from this action. And you can see on this diagram on photograph on the bottom left, they saved their harbour, and that was the town's main industry employer, was from fishing. And it's linked to the outside world, the main island of Iceland, for example. Other things they can do is there's some spraying water, and is in other parts of the world, like Hawaii, you can often try to divert the lava flows by building an embankment. Here it's labeled a dike, an embankment between you and the lava, with the hope that lava flow will take a different path. Here from 1960, they tried to, it didn't work. The lava kind of just came right through. And it often does, unfortunately. We're talking about solid rock here, molten rock. Here, later in 1989 in Hawaii, this is the visitor center, the Wahola Visitor Center of Hawaii, and sent it to the National Park Service. And here it was a lava flow approaching it, and emergency service workers trying to put out to cool the lava flow with water. It didn't work. Again, they just didn't have the volume of water to do that, and the visitor center was engulfed by lava flow and very quickly incinerated and lost. So they later had to build a new one. That lava from that 1989 date, if you look back at the dates, the previous slides, it kept on going day on day and eventually made its way to the ocean. So it was unstoppable, and that's usually the case for lava, but we try. Occasionally, we can change it in these methods. Last slide. So here's a lava flow, someone's property, for sale by the owner. Large, you can see a basaltic lava flow. This one on Hawaii, and yeah, he's given up. He's not going to live here anymore. This person, and they're trying to sell their house. Let's get out of there. All right, that finishes the final lecture on volcanoes. I hope you found them interesting. Hope you found them enjoyable. That's all for today, guys. Thank you for joining.